Hey everyone, it's question show time. Your questions, my answers. Apologies for not doing specifically question shows, although we've done a lot of the other content. It turns out doing the question show is like the most complicated one because it means like leaving the house to the backyard at least. And anyway, so we're back with question shows. Let's get into it. And stick around, we've got another guest answerer at the very end. All right, here we go. Mr. Villalobo. Can dark matter get so dense as to create a dark matter version of a black hole? So the first caveat, of course, is that we don't know what dark matter is. So can dark matter be a black hole? Well, we don't know what it is. So maybe if it's the kind of thing that can be turned into a black hole, but we don't know what it is, but maybe it can't if it turns out to be a thing that can't be turned into a black hole. So we don't know. However, here's what we do know, right? Which is that, dark matter was originally discovered a long time ago. In that its presence was detected. Astronomers were calculating essentially the rotation speed of galaxies, and they were looking at how fast the stars were rotating inside the galaxy. And what they found was that, you would expect, like say here in the solar system, that the planets all go around the sun at different speeds. Mercury goes the fastest, Earth goes slower, and Pluto, maybe a planet, maybe not a planet, goes the slowest, right? But in a galaxy like the Milky Way, the stars are all going the same speed. If they're going close to the core of the Milky Way, if they're going far away from the core of the Milky Way, they're going roughly the same speed. And the only way that astronomers could explain that is if you surround the entire galaxy in this halo of dark matter, right? That in fact, the matter that we can see is only about 1/5 of the actual matter that is inside the galaxy, and that's serving as this gigantic gravitational anchor that's holding the whole galaxy together. So, so astronomers said, okay, so maybe it's a particle, or maybe it's just gravity working at a scale that we don't understand. But then over the decades, science did more and more analysis. They did other kinds of surveys. And one of the most useful ones that they've done is this idea of gravitational lensing. So they look out into space and they look at how the light from distant galaxy clusters is getting distorted by the mass of stuff that's closer to us, right? And so the light actually takes this sort of curved path, this distorted path, like when you're looking down a hot road and you can see how the road is sort of wiggling and wobbling. The road isn't actually doing that, but the light is distorting the path that the light is making, right? The heat on top of the road. So astronomers were able to map out the quantity and the distribution of this dark matter, which started to move away from this idea that it's just we don't understand gravity at the largest sizes, but that there actually is some kind of particle. But then astronomers said, okay, so what kind of a particle is it? Is it something like that we already understand, or is it something else? We obviously can't see it, but does it interact in any other way? And so astronomers looked for examples where dark matter was interacting with itself. And so when you look at, say, two clusters of galaxies and they smash into each other, right? The stars, because they're essentially just little point objects, they pass right by each other like two gigantic swarms of bees. But the gas in the galaxies, that actually piles up in the middle. And so you'll get this example where these two galaxies pass right through each other, the stars pass right through each other, but the gas piles up in the middle and you get all of this sort of heated up gas that's in the middle. And so astronomers said, will the dark matter do the same thing? Will it pile up in the middle, and would we be able to detect it? Because they can see, again, that distribution. Watch how the light is being distorted. And what they found is, no, the dark matter does not bump into each other. It passes right through. And so that tells astronomers that probably the cross-section of whatever this particle is very small. Essentially, dark matter can pass by dark matter and not bounce into each other. So this is a long way of coming back around to this idea of, can you get dark matter into a black hole? And so while dark matter doesn't seem to interact with regular matter through any of the other forces, through electromagnetic radiation, through any of that, the one thing that it does do is gravity. It absolutely interacts with gravity. And so in theory, right, if you had a large amount of dark matter and you compress it into a small amount, it would have more and more gravity and more gravity, and eventually it would get so much gravity that it would turn into a black hole. And there's no reason to think that dark matter couldn't fall into a black hole and add to the mass of the black hole, based on, the amount of gravity that it's able to produce. So that's kind of like the current thinking. But again, we still don't know what it is. And so more evidence will be necessary to finally know once and for all what kind of particle it is, how does it work, how does it interact, and could it indeed turn into a black hole? Charmaine Rudy. If the universe is flat, how can it be expanding in all directions? Just the really easy questions for this week's question show. So when astronomers talk about this idea of the universe being flat, all they mean is that if you have two parallel lines and you head off in any direction in the universe, those lines will remain parallel for the duration of your journey. And you can sort of imagine bringing that same experiment here to planet Earth. You start off two people in cars, right? They set off and they begin to be parallel. And because as you follow essentially as you make a slice around a sphere, the Earth, the lines will actually expand out. Your two drivers on the car will go farther and farther apart. They'll reach the equator and then they'll come back close together and they'll crash into each other at the North Pole. And so two lines on the Earth are following a path that is not parallel. And that tells people essentially about the topology, the shape of planet Earth. The thinking is that if you go in any one direction, like I said, two parallel paths, they will remain parallel forever. And that has been essentially mapped out by astronomers looking at the largest scales. They've essentially made gigantic triangles, looked at huge triangles and made sure that those angles add up to 180 degrees. And that means that the universe is flat. But of course, the universe is three-dimensional, right? And so you have to be able to imagine a three-dimensional object that could be flat. And all that just means is that what is an example of a three-dimensional object where two lines could remain parallel forever? And I'll give you an example that should make sense, right? Think about a cube, right? If you have two parallel lines on a cube and they move parallel to each other, and then they'll go across one corner of the cube and they'll remain parallel, and they'll go across another corner of the cube, they'll remain parallel, and they'll return to the starting point, and they will have gone around the entire cube and yet remained parallel the whole time. And so that's one example of an object. Another example might be, say, like a torus. Like imagine a donut. Donuts. Where you can go anywhere around that donut shape. Parallel lines will remain parallel. Try it out for yourself. You'll see. So those are two examples of three-dimensional objects which have a topology that will allow for two parallel lines to remain parallel forever. And there are plenty of others, a 20-sided die, there's a whole bunch of these. And then there's maybe ones that we can't even imagine. So again, all astronomers know is that the universe is flat, but they don't know what its shape is, because it's very hard to sort of perceive the entire universe and really understand whether or not it wraps on itself, whether it's infinite or not. More research is necessary. David Schaefer. If and when we begin mining for minerals and other materials in space, how do you envision the politics of flooding the market with gold, copper, iridium, and other so-called rare earth metals? It's been said that if you take one asteroid, it can have as much platinum or palladium as has ever been mined in all the time here spent on Earth. And so all you got to do is bring one of these gigantic asteroids back to Earth and you destroy the economy for palladium or platinum or whatever. And all those people who bought vast stockpiles of platinum, it's worthless, right? You might as well just bought dirt. Well, here's the thing. It will probably never, and I mean never, I mean like within the next few hundred years, never be economical to bring materials back from space to Earth. That it will always be more economical to just go dig a big hole. Because all of the stuff that's out in space, all the stuff that's in asteroids, all the stuff that's in comets, it's here on Earth too. And it will always be easier, it will always be less expensive. As we develop new technologies to extract resources from the Earth, we will be able to do it in a place where we can breathe and where we can go home for dinner at the end of the day and where we can, we don't have to deal with gravity wells. The key is that those resources that are out in space will be used by people going out into space, right? When you imagine that every kilogram of gold or steel or copper or whatever it is you want to launch from Earth, it's going to cost you hundreds, thousands of dollars to launch per kilogram off into space. It will become more economical to just find this stuff out in space. Find it on the moon if you're going to be on the moon. Find it in an asteroid if you're going to be out in space and you're going to be doing manufacturing. And so really, the long-term advantage of being able to mine resources and gather these resources out in space is to get them from space so that we can use them in space. And chances are none of that stuff will ever come back to Earth. It's that it will just be able to save a tremendous amount of money to be able to manufacture stuff in space. Nitro 15. What would be a good set of binoculars for a newbie? Would they even be recommended for casual sky viewing? Any help would be appreciated. Yeah, I think if you're going to get into astronomy, get a pair of binoculars. That's one of the first things that you should do, because you can go out and you can see a lot of things with binoculars that you can't see with your unaided eye. The moon looks great. With good binoculars, you can even see, say, the rings of Saturn. You can see the moons of Jupiter. You can see a lot of really great fainter objects, globular clusters, open star clusters, Orion Nebula, Andromeda Galaxy. There's a lot of great stuff that you can see, and just like looking at the Milky Way is wonderful. So these are the binoculars that I use. They're Celestron 15 by 70 Sky Masters, right? They are they're great. They're sort of as big as you would want them to be. They're starting to get a little heavy, so I wouldn't recommend that you go any bigger. I know they do like a 25 by 75 or a 25 by 100. They're pretty big and heavy, and when you're holding on to them for a while, it gets very tiring. So I would not recommend that big of a set of binoculars. Normie Haddad. With all the deep sky surveys we've done, we must have at least taken enough pictures of Planet 9 to recognize it as such. Why don't we create a program to search through these images and find it automatically? Yeah, astronomers have absolutely done all sky surveys of the entire sky. They have imaged every corner of space, but it's all about at what brightness. So one of the most famous ones is the Sloan Digital Sky Survey that has imaged the entire sky. Astronomers use that for looking for quasars and galaxies and as a way to sort of compare a lot of things in space. Astronomers have also studied the plane of the ecliptic, which is sort of the region where all of the planets and all the dwarf planets tend to orbit within, at the level of brightness that they should be able to have found Planet 9. And so far, they haven't seen it. Now, that means that either it's too small, too dim, too far away, right? If an object could be bigger but farther away and still have that same gravitational impact. And the other possibility is that it's a little outside of the plane of the ecliptic and yet still be there, providing this influence. The observatory that's going to be able to find this is the Vera Rubin Observatory, which we've called, the Large Synoptic Survey Telescope. And this is the one that's going to be examining the entire sky every night at an incredibly faint magnitude, and that's going to be the instrument that's going to turn it up. So we're really just a couple of years away from the instrument that will find Planet 9. If it's out there, this is going to be the instrument. And it will also find every supernova, tons of asteroids, find comets before any other instrument. It's pretty much the observatory that I am the most excited about. Gordon Chin. What species will replace humans when we are gone in a few years? Well, here's hoping that we're not gone in a few years. Let's have like a couple more years than a few, maybe a few 100 years. That would be great. Who will replace us after we're gone? Well, that depends on how we go. Unfortunately, we're entering this realm now where human beings have the potential to cause existential crises that could, for example, eradicate all life on Earth. Maybe even damage the universe itself if we start up the wrong particle accelerator. Although the chances of that are super remote, right? Don't worry about it. But yeah, you can imagine if we wipe ourselves out by artificial intelligence, then that's who will replace us, is artificial intelligence. And if the artificial intelligence consumes all material on Earth to make robots, then there will be nothing else. So let's say that we don't wipe ourselves out with an artificial intelligence and instead, pandemic or climate change or something like that. I don't know if there's any reason to believe any of the other species on Earth, the ones that we haven't made extinct, can rise up and will become intelligent enough to have a civilization, right? I mean, there's a lot of very smart creatures on Earth. There's parrots, there's octopuses, there's chimpanzees, there's dolphins, right? So you've got lots of candidates for very intelligent species, but we don't know if tool use and language and the kind of sentience that we have as human beings is an inevitable outcome of a rise of intelligence. It might just be a fluke that we can do the things that we can do, and there's no expectation. And then the other thing is we've kind of made it difficult for any future civilizations who might come along, because we have extracted all of the resources which are easy to get to. We've dug all the iron that's easy to get to. We've cut down all the trees that are able to, so that you can burn them, right? We've gone after all of the oil, which was a huge kickstart to being able to raise our civilization up. And now we can only get at the oil thanks to an enormous amount of technology. And so how do you go from having, say, Stone Age technology, or like dolphin banging rocks together technology, to drilling for oil when all the easy sources of oil are gone? So it would take a long time for some follow-on civilization to be able to follow in our footsteps. We'd have to wait for the kinds of things that created all of those resources, plate tectonics, millions of years of phytoplankton falling to the bottom of the ocean and creating new deposits of coal and oil for them to start up their societies. And we know that was probably only about another 500 million to a billion years left before the sun heats up to the point that it raises the temperature on Earth, that essentially large life forms can no longer exist on the surface. Eventually the oceans will boil. And then, of course, 5-ish billion years after that, the sun will actually die, and then everything will be totally over. So it seems like it's up to us. So we really shouldn't screw this up. Arjun. Anyone else who found that interstellar comet with our robot orbiting it would definitely know something is up. Maybe this is how we say hello to the rest of the universe. So this is based on this mission we were talking about, how you send a spacecraft to orbit an interstellar object, and then if you can get close enough, you can get pulled into its gravity well, go into orbit, and then just continue to follow that object out into the universe. And you're exactly right. I mean, not only will you have a probe that has got a permanent location that's going to be orbiting around as it moves out into the universe, but it is like a beacon, right? That you've got this comet, this asteroid, something fairly detectable that someone in the future may go and find and examine to find. And of course, this is why astronomers were so excited about Oumuamua and Borisov. Was, here's an object that came from another star system. Maybe it's a spacecraft, maybe it's a solar sailing probe sent from another civilization. Probably not, but maybe. It seems like a great place to look. And so you would expect that in the future, some alien civilization who receives this new comet with our spacecraft orbiting around it says, we can learn something about the civilization that this comet passed through. And so this is another great reason for us to examine these objects as they make their way through our solar system. They are the universe throwing samples our way, and the least we should do is catch them and study them. Siddharth Chand. I always wondered, what if the Earth and Venus changed places size-wise? Earth and Venus are actually incredibly similar size. They are within a couple of percentages of each other. I think Venus is like 90% the mass and size of Earth. So essentially it's the same size and mass as the Earth. And so if you made Earth like a little bit smaller like Venus, not much would be different. If you made Venus like a little bit bigger like the Earth, not much would be different. It's their location in the solar system that is the big problem. If you move Earth to the same orbit as Venus, then it would have the same kind of runaway greenhouse effect that Venus did, probably. And if you took Venus and moved it out farther from the sun, maybe it never would have gone through this runaway greenhouse effect in the first place. So it's all about location, your distance to the sun. And for what astronomers think, in fact, we are actually at the very inside edge of the habitable zone. So essentially the zone where, in the solar system, where liquid water can exist. It ranges from just beyond the orbit of Venus to around the orbit of Mars. But the Earth is orbiting on the inside of that zone, which is why if we were any closer to the sun, we probably wouldn't have a very habitable planet at all. Ted Geishman. Not a scientist, but why do we need a reason for the expansion of the universe to be accelerating? If the edge of the universe is accelerating away from the Big Bang center of all speed of light, all matter is trapped in space-time, and we will go along for the ride. Thus, things farther from us will look to be accelerating because they are. So you're imagining the Big Bang and the expansion of the universe as an explosion, right? You're imagining there was this point in space and then suddenly, kaboom, this whole big explosion went out. And yeah, wherever you are, you're watching things go away and they are accelerating as they're moving away from you, from your perspective. That's what it feels like. But that's not what the Big Bang is, right? The Big Bang is, and I bring this up every couple of episodes just to make sure that I can sort of lock this into people's brains. Imagine a grid that goes on forever in all directions. The grid could be infinite. And so there is a certain density in each part of the grid. And a long time ago, at the beginning of the universe, the size of the grid, the density of the objects in that grid was smaller. The grid was smaller, the places were denser, and then over time, the grid got larger and the amount of material in this grid got less and less dense. And so if you're on sort of one of the nodes, if you're one of the corners of any of these parts of the grid and you're looking away, it appears that everything is moving away from you. And if you go to any other location, it appears that everything is moving away from you as well. And so when we look out into the universe and we see everything moving away from us, either we're at the center of the universe, which would be very bizarre, a crazy chance, or everybody sees the same thing, which is the universe moving away from them. And that's what you would get if you had this universe that was just getting less and less dense over time. And so then the question is like, well, what does it mean? Like, why does the universe have to accelerate? Well, the universe doesn't have to do anything. The universe just does what it does, and we are detecting it, right? But if the universe is expanding, and we don't know what set off that expansion in the first place, but you would expect it to be coasting to a stop, because all the mutual gravity of all of the objects that are inside of it are going to be pulling at each other, and you would expect essentially the expansion of this gravity to slow, or the expansion of the universe to slow down and coast to a halt. And then maybe even all these objects in the universe would come back together and smash into each other, right? And so astronomers have been attempting to work out the rate at which it is slowing down. And what they found was not only is it not slowing down, but it's actually accelerating. And the analogy that I always like to use is you take a ball and you throw it into the air, right? And what you would expect is the ball would come back down into your hand, right? The gravity would be pulling it back down. So imagine, all these galaxies, their gravity is pulling at each other and it's going to pull them back together. But instead, you throw the ball up into the air and the ball accelerates off into space. That would be weird, and yet that's what seems to be happening in the universe. Galaxies are, every part of the universe seems to be, have this repulsive force that is accelerating every part of it away from every other part. And it is absolutely a surprise, not predicted by anyone, not the kind of natural expectation that you would see, and yet there it is. And that's dark energy. So the universe just gets to be as weird as it wants to be, and we don't really have any control over it. We just have to try and understand and figure it out as we go along. Josh M. Do you think NASA is moving too fast with the Artemis program? I think it's great NASA is pushing to get back to the moon so quickly. I would love to see a moon base in my lifetime. But do you worry that NASA is pushing too fast? Well, we're recording this episode in 2020, and we are about 50 years since the last human being set foot on the moon. So are they returning to the moon too quickly? I think they've been taking their time to be able to do this. And when you think about sort of this current race to the moon by 2024, this has been in the works for 2 decades-ish, right? With the Constellation program, and then that moving into the Space Launch System, and now into the Artemis program. So NASA has been working, and whether it's to go to an asteroid, whether it's going to send people to Mars, whether it's going to be to go back to the moon, NASA has been working on the next generation of launch systems and platforms and spacecraft and landers and all this kind of stuff. The exact timing, NASA had been very kind of fast and loose about the timing, and mostly that's just because they got a lack of commitment and leadership from the government. The government was like, we're going to go see an asteroid. No, we're going to go to Mars. No, we're going to go back to the moon. No, we're going to go, right? They just go round and around. And so finally, the government said, no, we're going to go to the moon, and they picked a date which sort of coincidentally should end within someone's second term, should they be elected for a second time. So it's possible this is a bit of a PR stunt, but NASA is very safety conscious, and they will absolutely not be taking any risks with the people, with their, with the spacecraft, with the hardware, in trying to complete this mission. They feel like achieving humans landing on the surface of the moon by 2024 is achievable within the current state of the technology. But already we're seeing the Space Launch System getting delayed. We're seeing the effect of the coronavirus rippling through the administration and everybody's budgets and taxes and timing and all of that. And it feels like there's no way that's not going to have an impact on the timelines, which already would have been difficult in the first place. That said, there's a lot of really exciting new technology. There's what's coming up with Blue Origin and their New Glenn rocket. There's obviously SpaceX with the Starship, which could just literally just go do it, right? Just fly to the moon, land, come back. NASA buys some flights and they get to go to the moon and return. So we are still waiting to see how all of this plays out. And I think that NASA's not going to take any chances with the safety of their astronauts. And say it takes 2 extra years. Say you don't get there till 2026, or maybe you get there at 2028. That's still better than 50 years. So I don't think anybody's going to cut corners and launch when it seems overly risky. And even if they do launch later on and it happens a couple of years later, when you think about how long we've waited, it's fine. Take your time. Let's go back to the moon this time to stay, right? I want to see a base like Antarctica, but on the moon. Right now, I can look up into space and know that there are astronauts flying overhead and have been doing that for more than 20 years. I want to see that on the moon, and eventually I want to see that on Mars. Let's have a permanent presence out there in space in a way that's safe and is sustainable for the long term. Not boots on the ground and coming home, but to stay. Steve Blandmeg, would an electric leaf blower work to clear your paved landing pad on the moon? We talked about this idea of how rockets landing on the moon are going to kick up regolith, and in fact this stuff's going to go up into orbit and it's going to cause this sort of cloud of particles that spacecraft trying to orbit around the moon could impact and be damaged. And so you want to create a landing pad, probably with regolith in some way, and then you want to keep it clean so that as your rockets land, they're not kicking up this regolith into space. A leaf blower wouldn't work because a leaf blower sucks in air from the atmosphere and then blows it back out at a higher velocity. There's no air on the moon, so you can't take advantage of that atmosphere to do that. Probably a broom is going to be the thing that works the best. You're just going to go out there and you're going to sweep it off. But don't worry, right? Because it took billions of years for the regolith to accumulate on the moon. And so as you've built your landing pad, you're going to get a light sprinkling of regolith over tens of years, hundreds of years. But it's not going to be a tremendous amount falling down all the time. And I think this dust management, right? I think you're going to see on the moon, NASA is going to be clearing off chunks of the moon which are regolith free, and you are expecting almost like a clean room, like these parts of the moon we can move around on and not expect to encounter a lot of regolith, and those parts are out in the regolith zone where you have to take extra precautions to deal with it. Building with Todd. Hey Fraser, is it possible to have a solar system with no star? Perhaps that is a massive gas giant or rocky planet at its center, and the planets orbit and spend all of eternity in darkness. Great question, and we have a guest answer, another from the American Astronomical Society. This is Dr. Natalie Hinkel. She works for the Southwest Research Institute, specializing in exoplanets, and she has an answer for you.
It's a very optimistic question. So yes, it is possible to have what we call free-floating planets. So they don't have a host star. Sometimes they're gas giants, sometimes they're rocky planets. The problem is going to be that they'll be very cold. We really need the sun's light and the heat in order to have life and to maintain a lot of biology on the surface of the planet. So if you have a planet without any kind of host star, then this planet's going to be fairly cold. But that doesn't mean that there couldn't be life. There are certain elements within the inside of planets. For example, rocky planets, they have radioactive elements, and that will actually heat the planet. In fact, we needed on the Earth to have aluminum-26 and iron-56 in order to heat the planet just enough so we actually can have continents and not just a total water world. So it's definitely an interesting question, and there's extreme examples. But yes, there could be those planets, and they could maybe have some life.
All right, thanks, Natalie. That was amazing. Again, I really appreciate you taking the time to answer the questions from the viewers. All right, I hope you enjoyed this week's question show. As always, wherever you are across my channel, if a question pops in your brain, write it down. I'll gather them up and I'll answer them here. And I will see you next week. Soon. I'll see you in the future.